corporate members, students, guests, ladies and gentlemen. Although no lady still now is present here, it's customary. It's my great pleasure and honor to welcome you all at the webinar on optical fiber communication, organized by Electronics and Telecommunication Engineering Division of West Bengal State Center. You must be knowing that the Institution of Engineers India is a statutory body to promote and advance the engineering and technology. It was established in 1920 and incorporated by Royal Charter in the year 1935. It's the largest multidisciplinary professional body of engineers, encompassing 15 engineering disciplines with a membership strength of more than 8 lakh. It is serving the nation relentlessly for more than a century. The Institution of Engineers India has its headquarters located in Kolkata. It's our proud, with national presence through more than 100 centers, 6 overseas chapters, and 9 forums. The latest forum of Institution of Engineers is Disaster Management Forum, which is located at Dehradun. The Institution of Engineers issues Chartered Engineer Certificate to its corporate members, by virtue of which one can impaneled in the original side of high courts, central excise and customs, and other similar government concerns, and professionally act as a chartered engineer to solve various problems. By virtue of being a full member of the International Professional Engineers Agreement since 2009, the Institution of Engineers India represents India and has been empowered to establish and maintain the India section of the International Professional Engineers Register. The International Professional Engineers registered with IEI may receive credit when seeking registration or licensure in the jurisdiction of another member. That is, this will facilitate an engineer in mobility across member jurisdictions, which includes countries like Great Britain, United States, Australia, Canada, New Zealand, South Africa, and many more. In order to promote the research and development work in the field of electronics and telecommunication engineering, the Institution of Engineers publishes Journal of the Institution of Engineers India, Series B, in collaboration with Messrs. Springer, which is an internationally peer-reviewed journal. The journal is published 4 times in a year and serves the national and international engineering community through dissemination of scientific knowledge on practical engineering and design methodologies pertaining to electronics engineering. As because the journal composed of other 2 engineering divisions, that is electrical as well as computer science, so the articles published in the journal encompasses a wide range of fields such as power system, power electronics, instrumentation and control, high voltage engineering, energy studies, communications, circuits and devices, antenna and microwaves, computer architecture, algorithms, signal processing, image processing, computer communication networks, database system, to name a few. Original manuscripts are published through double-blind peer review in this journal. Various types of technical activities organized by the electronics and telecommunication engineering include All India seminars, All India workshops, lectures, panel discussions, etc., which are held at various state or local centers of the institution. Because of the pandemic, IEI never stopped its technical activities. All these seminars and workshops, lectures, etc., what just I have told you, for the last 1.5 years, we are organizing all these programs, all these technical activities online. National Convention of Electronics and Telecommunication Engineers, an apex activity of this division, is also organized in each year on a particular theme approved by the Council of the institution. In the National Convention, several technical sessions are arranged on the basis of different sub-themes along with a memorial lecture, which is delivered by the experts in the field. And in tune with the objective of Division Board, the Electronics and Telecommunication Engineering Divisional Committee of West Bengal State Center has organized this evening program or panel discussion on optical fiber communication. I wish the webinar a great success. Thank you. Have a wonderful evening.
Thank you. Thank you.
From the mute, Achu.
Thank you, Mr. Chairman, for your welcome address. Professor Kamal is no longer available, I could see. He was there a few minutes ago. Okay, let us proceed with the program. May I now request, Professor Kamal is there. Professor Kamal, may I request to kindly address the audience?
You asking me?
Professor Kamal.
Professor Dr. Tara Singh Kamal, Chairman, Electronics and Telecommunication Board, Institute of Engineers, India. Kindly address the audience.
Dr. Kamal, can you hear us?
It appears he is not
Dr.
unable
Kamal?
to. Oh. Again, he is out. Okay, then let us proceed with the webinar. May I request our joint convener, Mr. Chanchal Chakraborty, to introduce the panelists to the August audience.
Good evening, everyone. Today, we are going to organize a panel discussion on optical fiber communication. As you know, that is the available as a broadband media, which is completely suitable for internet services, for 4G services, upcoming 5G services, and above services, whatever will be coming next. So without knowing optical fiber, we cannot proceed further. So today, we'll be having a discussion which will be split into two parts, optical fiber communication. The first part will be optical fiber system, which will be delivered by engineer Avijit Ghosh. Now, Avijit Ghosh is a BTech, and his core skills are stakeholder management, project management, network planning, network operation and maintenance, team management, learning management systems, and process documentation. He has worked previously in Huawei Communication and Tata Teleservices. He is having a rich experience of 15 years, and he is now currently acting as a state training head, Reliance Jio Infocom Limited, West Bengal South. Our second panelist today is Mr. Devamay Bhattacharya. Now, Devamay has completed B from Jadavpur University, and he has worked in the telecom transmission for more than 30 years under Department of Telecommunication and in BSNL. At present, he is acting as a divisional engineer of BSNL posted in Calcutta Telephones. He is having experience in network planning, installation, commissioning of PDH systems, SDH systems, MLLN systems, higher order digital cross connects, DWDMs, and so on and so forth. He has acted as a nodal project head for the new CPAN and OTN technology, which has been introduced in BSNL in recent past. Because of his outstanding contribution, he has been conferred with Visis Sanchar Seva Padak in 2013. Now today, as we have told, this optical fiber communication has been split into two parts. The first part, optical fiber system, will be handled by our first panelist, Mr. Avijit Ghosh. And second, we'll be talking about optical transport network, on which our engineer Devamay Bhattacharya will give the presentation. So with these things, I conclude it here. Now the platform is for the panelists.
Just 1 second. I want to request Professor Tara Singh Kamal once again. Professor Kamal, are you in a position to hear us? Professor Kamal, can you hear us? Shruti, follow. Okay, thank you so much. Professor Kamal আসছে যাচ্ছে ওনাকে পাচ্ছি তো না আমি। প্রফেসর কমলকে একবার আসছেন আবার চলে যাচ্ছেন। ও আচ্ছা, তাহলে ছেড়ে দাও, তাহলে আমরা কন্টিনিউ করে যাচ্ছি, কেমন? আচ্ছা ঠিক আছে, ওকে 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 ওকে, থ্যাংক ইউ। থ্যাংক ইউ সো মাচ। রাত তো কিছু তুমি শিখিয়ে দিয়েছো আমাকে, থ্যাংক ইউ সো মাচ। ওকে ওকে দেন, বাই বাই বাই। May I now request Engineer Abhijit Ghosh to start his presentation?
Thank you so much. Thank you so much. I am really very much honored to speak in front of such august audience. So without wasting my time, introduction part has been already given by Chanchal sir and other sirs. So I will just straight away start my topic today. So I will discuss about the basics of optical fiber today. And the flow will be topics like I will discuss about the optical fiber architecture, and then the types of cables, and the fiber laying techniques, different types of connectors and all. So let me present my screen, and hope I'm audible to everyone, right?
Yeah,
Audible.
yeah, Vijit, you are audible.
And the presentation is visible to everyone.
Yes.
Absolutely.
Thank
Make
you
it
so
in
much.
presentation mode.
Okay, thank you so much. So the first topic is basics of optical fiber communication. So fiber optics does not actually need any introduction in today's age, because it has become an impeccable part of the entire networking industry, especially if we talk about the telecommunication. The requirement of the bandwidth, the high-speed data requirement is growing every day. Our television, our telephony system, everything requires a huge bandwidth, so which can be only possible with the help of this fiber optics, which has replaced our old copper cable systems. So we'll learn about the architecture of fiber optics, how the fiber optics looks like, a cross-sectional view. So fiber optics is nothing but a thin strand of glass. It's a strand of glass, thickness of which is comparable to our human hair, which is about 50 micron approx, through which we send our data information with the help of light signal, optical light signal, right? So if you talk about the geometry of the optical fiber, it has 3 layers. The inner layer is the core layer, and the above core we have the cladding layer. After that we have coating layer. Now core layer is the layer through which the optical signal passes through the optical fiber. It is the layer through which the signal passes, and above which the cladding layer, which helps the light signal to remain inside the core layer without being refracted away to the other layers. And the final coating layer helps to protect the optical fiber. It is the protective layer for the entire optical fiber. Now it varies from vendor to vendor, the different makes of optical fiber. They give different coating layers to prevent the optical fiber from different environmental conditions. So like you can see the right side image, there are few coating layers mentioned, like the primary coating layer, secondary coating layer. Then there are aramide yarn layer, which gives a tensile strength to the entire optical fiber. And then finally we have the PVC coating layer. the thickness of the entire optical fiber is around 250 micron. But if you talk about the core and cladding layer, which is the actual optical fiber, coating layer is just protecting the optical fiber. So the diameter of the core layer varies from 8 to 62.5 micron. And the diameter of the cladding layer is about 125 micron, right? Moving to the next slide. Now, since we are talking about light signals, we transmit the data with the help of light signals. So definitely, it becomes important to talk about the optical spectrum through which we send the light waves. The frequency with which frequency or the wavelength, basically optical spectrum is nothing but our electromagnetic spectrum, which is a huge range. We have our X-rays, we have our visible light signals, all comes under this optical spectrum, within which we use the infrared region to transmit the data in telecom industry. Visible lights can also be transmitted through optical fiber, but in telecom industries, we use the infrared region. Now, if you, the diagram in front of you, it starts from the left side, it is UV rays. Then after that, our visible range is there, which is up to approximately 700 nanometer. After that, the infrared region starts. So what happens? Basically, the wavelength of the electromagnetic ray increases from UV towards the infrared, from ultraviolet towards the infrared. So electromagnetic spectrum, few of the electromagnetic waves we can specify with the help of frequencies, we can specify with the help of wavelength as well. So generally when the frequency is on the higher side, then we specify the wave with the help of the wavelength. When the wavelength is on the higher side, then we specify it with the help of frequencies. So both are, we can denote a electromagnetic wave with the help of frequency as well as wavelength. Okay, but the infrared region we generally specify with the help of wavelength. So it starts from 800 nanometer approximately and ends around basically in the communication purpose we use till the 1700 nanometer, but even infrared region is extended even after that. But we use for the communication purpose, we use from around 800 nanometer to 1700 nanometer. This is the range of the spectrum through which we transmit our data. Okay, now this entire range are again further divided into different bands. So the popular bands which starts basically we have the 850 band, and then after that this from around 1250 nanometer to 1600 1700 nanometer, there are specific bands like O band, E band, S band, C band and L band. So these are the bands through which the communication happens. O denotes the original band which was previously used to transmit the data. Initially when fiber optics was invented, at that time O band was the most popular. That's why it was called original band. And then after that, this E band and S band, basically the loss you can see if we make a graph against the loss versus the wavelength, then more the wavelength, the loss through the optical fiber decreases. The transmission loss through the optical fiber decreases. So the highest loss, if we talk about the wavelength 800 to 1700, then from 800 towards 1700, the loss gradually decreases. The curve shows that. Now, now O band was initially basically, now use of this band also depends not only on the optical fiber, on the invention of the end equipments as well, like the SFPs and all. I will talk about in the later slides. So initially this O band, which ranges from around 1260 nanometer to 1360 nanometer. The SFPs and the connectors were compatible to work with this wavelength. Then later on, invention proceeded, and the S band and C band got more popularity. Most of the optical devices started, means whatever the inventions or the fabrication started happening, they were started to make those in S and C band. And the loss in the C band is the least. Loss in the C band is the least. L is the long band, which can also be used if the C band gets exhausted. But since the invention of the SFPs and the connectors were more in the C band, so basically C band is the most popular for the long distance communications. For NLD intracity communications, we use the C band the most. But S band is also used in the FTTX network, specifically if I can talk about in FTTX network, the downlink traffic, is transmitted through the S band spectrum range, which ranges from around 1460 to 1530 nanometer. So in this way, we have divided into different optical bands you can say, and the different vendors who are making the optical fibers or the SFPs connectors, they make those keeping in mind this optical band so that the losses through those are minimum. Now, optical fiber has several, positivities why we use optical fiber, why the copper cable has been replaced by optical fiber. Nowadays, almost all the operators have connected their backhaul network wherever the networking is happening, or everything is happening through optical fiber. Now, what are the most positive features which makes this optical fiber so popular these days? So first and foremost, what I want to talk about is the bandwidth. It is the most, and it's the most number one important point which made the optical fiber important, because with the advent of the technology these days, the transmission of data for a longer distance, more and more information needs to be transmitted for a longer distance. This is the requirement. So we need a wide bandwidth, which is possible through the optical fiber. Why? Because because we transmit the data through the light wave. So light wave, the speed of the light, 3 × 10⁸ meter per second. So it's very fast. So that is the reason why, the bandwidth, we can provide a huge bandwidth through optical fiber. So wide bandwidth is the important feature. Next is a low attenuation. So it's not only that the signal can be transmitted for a longer distance, we have to also keep in mind that the losses, attenuation means loss. So the transmission loss is less. So the optical fiber, since we are using a technology called, a total internal reflection, so the power loss through optical fiber is very, very, minimum. So we can say the next important feature through optical fiber is low attenuation. Next is electromagnetic immunity, which is also a very, very important point to be discussed. The data is transmitted through light wave. Initially, when the data used to get transmitted through copper wires, it was transmitted through electrical signals. So everybody knows when the signal is transmitted, electrical signal gets transmitted through a copper wire, an electromagnetic field is produced around it, which creates interference. If two copper wires are placed parallel to each other and the signals are getting transmitted through both the wires, then interference happens one signal will interfere the other. But this kind of magnetic field does not happen in case of optical fiber. So you can say it is, immune to electromagnetic interference. So that is the reason why optical fiber is used in the high tension electrical poles in order to, manage the nodes from the back end. The electricity boards or the other electrical poles, they manage the nodes through the optical fiber, and those can be laid parallel to the high tension optical copper wires, the high tension electrical wires. Why? Because there is no interference. Next, in small size. So I have already talked about the size. It's the entire, including the coating layer, it's 250 micron. So the size of the optical fiber is very small, and it is very light in weight since it is made up of glass and plastic materials, the coating and all. So it is very lightweight. So the installation works becomes very easy. It can be handled very easily. I can say a kilometer of optical fiber will weigh maximum 5 to 6 kgs. It can vary from different makes. It can vary a little bit, but approximately it is so. So it can be carried in hand as well, a kilometer. But if we talk about copper wire, it's very, very heavy, almost 10 times heavy. So that's a very important point. Next is safety. Safety, since it is made up of glass, optical fiber, most of the optical fibers are made up of glass. There are plastic optical fibers as well, but for telecommunication purpose, we mostly use the glass-made optical fibers. So they are not reactive to any of the chemicals, or there is, less chance to get electrical shocks because of, weight hand. You are touching the, like initially in copper wires, there was, if there is any child in home, so they will hold the cable and they can get electrical shock. So all those things, it's very safe and secure. Data cannot be theft easily. In copper wire, initial days, if we think about, in landline phone, when the connectivity used to be done with the help of copper wire, people could able to tap the signal, and the only thing is they need a receiver to hear the voice, whatever the communication is going on. But through copper optical wire, this is practically impossible, because yes, definitely somebody can, cut the optical fiber, splice it with another, and they need a lot of decoding devices. So it's practically impossible, because even for doing that, it requires a huge investment. So theft is practically impossible in case of optical fiber. So it is very secure, reliable, easy to installation and maintain, that I have already said. And the 10th point, upgradability. This is a very, very important point, which made this optical fiber even more popular. Now, when a network is built, all the nodes are already connected, kilometers of cables are connected, laid and connected with each other. Now, suddenly there is a requirement of upgrading the bandwidth in the network. Now, with optical fiber, since it gives a huge amount of bandwidth, we are not able to use that much amount of bandwidth, because our end devices are yet not, invented to, compete with that much of bandwidth which an optical fiber can get. So only by changing the end devices, that is the SFP or the connectors, we can upgrade the bandwidth very easily. Suppose a length of a kilometer connectivity, suppose it was a 1 Gbps connectivity, and now we want to upgrade it to 10 Gbps. What we need to do is, we need to change the end devices, that is the SFPs, which is compatible to 10 Gbps. The optical fiber will take that much of bandwidth. So no need of changing the entire cable, which in case of copper wire, if suppose a cable of 100 Mbps, we want to change it to 1 Gbps, we need to change the entire cable those days, right? But that is not required in case of optical fiber. So the upgradability is very easy. That made optical fiber a very popular. Now, the last and important point is very good price to performance ratio. Now, a cable, optical fiber cable or a copper cable, almost they will cost similar in market. But if we talk about the performance, price to performance ratio, because the same cost cable, same 1 kilometer cable, let's talk about that, the amount that will cost, but the bandwidth will get through optical fiber will be huge. Also, in case of to set up the network, in case of copper wire, we need to place amplifiers in between, right, to boost the signal. Very frequently we need the amplifiers to amplify the signal, because the loss through copper wire is much more. But in case of optical fiber, we can send signal up to 100 kilometers, 200 kilometers without a very less amount of loss. So after 100 kilometers, we may need to put an amplifier. So to put an amplifier, that also needs to be installed in a facility. So all those also cater to a cost to set up the network. So that's why we can say that the price to performance ratio is very high, very good, comparable to the copper cable. So these are the important points which made fiber optics very popular. Now, about the principle, how the optical fiber works is very common, and it's everybody of us have studied. So it's a total internal reflection, we call it. So what is the principle? When a light ray travels from a higher density to a lower density, what happens? It gets refracted away from the normal axis. It gets refracted away. So if we keep on increasing the incident angle of the light ray, a time will come when the light ray will start to travel parallel to the medium. So that particular angle, the angle at which the light ray starts to travel parallel to both the medium. In this case, the two mediums, we have taken an example of water and air, where water is a higher density layer and air is a lower density. So the refractive index of water is higher than the air. Now, the angle at which the light ray is starting to travel parallel to the water and air, that particular incident angle, we call it critical angle. Now, if we keep on increasing the incident angle, then what will happen now? The entire ray will get reflected back to the same medium. It will not get refracted to air or the other medium or the less denser medium. Rather, it will get reflected back to the same medium. So this particular principle we use, you can consider, if we talk about optical fiber, you can consider this water layer, the core layer of optical fiber, and the air, a cladding layer of optical fiber. So the density of the core layer is higher than the cladding layer. So the refractive index of core layer is higher than the cladding layer. So when a light ray is traveling from the core to the cladding layer, and if we inject the light ray inside the optical fiber with an angle more than the critical angle, then what will happen? The light ray will keep on reflecting inside the core layer, and same way it will reach the far end. So without getting refracted away from the medium. So that is the principle with which optical fiber communication happens. Now, here are a few applications of optical fiber. Other than telecom industry, optical fiber is widely used in many other sectors, like, as I already said, in electrical sector, like the electricity boards, like in West Bengal, our WBAC. So like that, every state has electricity boards. So they maintain their nodes. They make these nodes visible to the back end, their NOC people, we call in telecom industry NOC. So whatever, they are backend people who are monitoring their nodes. They make this visible with the help of optical fiber because of that electromagnetic immune property of optical fiber. So that can be laid parallel to the high tension electrical wires. So that with that, it can be monitored. Next is military, definitely because of the secure transmission through optical fiber. It is widely used in army, military. There are different medical fields where medical, therapies, endoscopy, and different surgeries are happening with the help of optical fiber. And nowadays, many microprocessors are getting fabricated. Instead of the copper fabrication, they're using optical fiber. Why? Because of, again, that electromagnetic immune property, and another thing is the reactivity property. Since copper wire gets, corrosion effect, there is a corrosion effect in copper wire, which is not there in optical fiber. So it does not react with atmospheric oxygen and all. So the life of optical fiber is longer than the copper wire. It is almost, we consider it 30 to 40 years. If it does not get cut, the life, it will remain intact, right? So these are few examples where optical fibers are used. Now coming to the different types of optical fiber. So sorry. So coming to the different types of optical fiber, broadly we can say optical fibers are of two types: single mode and multi-mode. So what is this single mode and multi-mode? Single mode, by the name you can understand, mode means light ray, that is a ray. So single mode is a single light ray. Single mode optical fiber are those through which only a single mode of light or a single light ray can be, injected and passed through. So that is single mode. The core diameter of the single mode is very less. It is approximately 8 to 10 micrometer. Rather, in case of multi-mode, we can inject multiple number of light rays through the fiber. Why? Because the core diameter in this case is much wider. It varies from 50 to 62.5 micrometer, which allows multiple rays of light to get injected inside. Now in telecom industry, most of the transmission lines, if you see, we use single mode optical fiber. Why? Because the loss through the single mode is less. There is no interference loss within the intersignal loss happens. So that's why we can, the light ray can travel up to kilometers, hundreds of kilometers through single mode fiber. Rather, in case of multi-mode fiber, since we are injecting multiple number of light rays, so they will interfere among each other because these are similar rays, and which can create loss, and that's why the signal cannot travel longer distance. So multi-mode optical fiber we generally use where the connectivities are of shorter distance, like in same premises. If we want to connect between cabinet, different sub-racks of nodes, so that can be done through multi-mode fiber. But otherwise, single mode fiber is mostly used everywhere in the transmission lines. In microwave, I can give you an example of multi-mode fiber. If you have seen a microwave connectivity, the baseband unit and the antenna gets connected with the help of multi-mode fiber, which will be not more than 100 meters maximum. Okay, there we can use multi-mode. Now, by seeing into the bare eye, how will we understand that the fiber is a multi-mode or a single mode? So generally the vendors which are making this optical fiber, they fabricate two numbers on top of the optical fiber. First number indicates the core diameter. Here you can see 50 slash there is no, anyways. So 50/125. So the first number indicates the core diameter and the second number indicates the cladding diameter. So now everybody knows that for single mode, the core diameter is within 10 micrometer, and for multi-mode, the core diameter is minimum, it is 50 micrometer to 62.5 micrometer. So wherever this first number is more than 50, you can understand easily that this is a multi-mode optical fiber. But in this case, you can see the number written on top of the optical fiber is 8/125. See, the second number is the cladding diameter, which is same in both the cases, for single mode as well as multi-mode, which is same. But the difference is in the first number, which indicates the core diameter. In this case, it is written 8. So it is less than 10 micrometer. So we can understand easily that this is a single mode optical fiber. Now, these are the different ITUT standards. Each of these standards have different characteristics of optical fiber, based on which different vendors makes their optical fiber based on these specifications. The most popular one among these is G.652D. Most of the operators use G.652D optical fiber. Why? Because here the wavelength range is 1310 to 1625, which is mostly used for single mode optical fiber. Okay. Other type of optical fiber, I can say this G.657A, 657B. These also we use nowadays. A very popular technology is the FTTX technology. So fiber to the home. So fiber to the home technology, wherever the fibers are routed inside the customer's home to connect the router. So there are a lot of bendings inside the room. So there we use this G.657A and B, which allows a little bit higher bending. Otherwise, the other standards of optical fiber does not allow much of bending, which can create a loss. So this is a little bit about the ITUT standards. This is open in the internet, so it can be studied from the internet very easily, all the specifications for all different ITUT standards. Now, that was about the optical fiber basics. Now, I will talk about the cables. Now, optical fibers are available in market in the form of cable. We don't lay a single optical fiber for kilometers. We always bundle it into certain number and form it a cable and then lay it. So we'll talk about what are the types of cables available in the market. So before talking about the cable, it's important to understand the color coding of optical fiber. This is an international standard which starts from the color blue and ends in aqua. So there are 12. So this sequence remains fixed for, this is an internationally fixed standard for all the types of cables. When we bundle all the optical fiber together, we have to understand the number of optical, which optical fiber inside that cable we want to work, we want to splice, we want to do. So for that, to understand that very easily, we follow this color coding system. This starts from blue. Blue will be always number 1, orange number 2, green, dark, gray, white, red, black, yellow, violet, pink, and aqua. These are the 12. Now, the right side tube color coding also remains the same. Now, this will be better understood if I talk about the cable in my later slide. So let me move forward, and this color coding will be understood more easily. Now, the first type of cable is the loose tube cable. This, the example which I have put in this slide is a 48F loose tube cable. Now, by the name, it can be understood that this particular cable contains 48 number of fibers inside it. So that's why the name is 48F. Now, how the optical fibers are bundled inside this cable, let us see. These circles inside there, you can see 1, 2, 3, 4, 5, 6. These indicates basically the tubes. the inside part is filled with a gel, a filling gel. You can see this sky blue color, inside which these tubes are loosely floating. That's why we call it loose tube. This is loosely floating inside this gel. Instead of compact thing, it is loosely floating. So the color of the tube, you can see, it starts from blue, orange, green. If you go clockwise and start from the blue color, blue, orange, green, brown, gray, and white. Now, if you come back to this color coding slide, you can see the right side tube color coding. So we will consider the blue tube as the number 1 tube, the orange tube as the number 2 tube, then the green, brown, gray, and white. So this particular cable is having 6 tubes in it, and the number 1 tube is blue, number 6 tube is the white. Now inside, if now this 48 type of cable, this particular cable, it can vary from vendor to vendor, but this particular cable is having 6 number of fibers inside it. So I'm so sorry, 8 fibers inside each of the tubes. So each of the tubes are containing 8 fibers inside it. So total number of fibers are 6 into 8, 48. So if you talk about the color coding of the optical fibers which are present inside each of the tube, so there are 8 optical fiber. The color of each of the optical fibers will be starting from blue and it will end at black. So the first fiber will be blue and the 8th fiber will be black. So the same color fiber will be present inside each of the tube. So that is how the engineers who are working in the field, who are working on the fiber, suppose there is a fiber cut, now which fiber has got cut, so he needs to find it out, splice it, and may fix it. So those things are handled with the help of these color coding system. Now this 48F, okay. Now the next type of cable is ribbon type. That was loose tube. It was loosely fitted, and the fibers inside the tube were also loosely floating inside the tube. Now in this case, ribbon type, here also you can see the inside part is having few number of tubes. Now here 2 examples are given, 96F and 288F. So by the name again, you can understand the left side image is of 96F, which is having 96 number of fibers inside it, and the right side it is 288F, which is containing 288 number of fibers inside it. Now why we are calling it ribbon type? Let us see. For the 96F, you can see there are 5 tubes, but the 5th one is a filler in this case. So effective tube is 4. Filler is used just to maintain that circular shape. So the 4 tubes are there. So the number 1 tube is blue color, second tube is orange, green, and then the brown. So 4 tubes are there. Now inside each tubes, previously the fibers were directly put inside the tubes, but in this case we are not putting the fibers directly. We are again bundling 8 fibers into ribbons. So there are 3 ribbons inside each of the tubes, and each of the ribbons are having 8 fibers bundled together. So the picture of a single ribbon is given in the right side. You can see all the fibers are closely held, and it is tied up with the help of several ribbons, and that ribbon, so each tube is having 8 into 3, so 24 number of fibers. So you can understand, initially in case of loose tube, we were getting only 8 number of fibers inside each tube, but in case of ribbon type, we are getting total 24 number of fibers. So the entire 24 into 4, it will give you 96F. So now, why these 2 types of fiber cables are required and where we use these? So wherever, so you can understand that ribbon type cable is having more dense number of fibers. So the number of fibers is much more in case of ribbon type of cable. With the help of this ribbon system, we could able to put more number of fibers inside the same diameter of the cable. So wherever in our network we need a dense or more number of fibers, so there we use ribbon type. So I can tell you in most of the operators, although it can vary, but still I can say you in most of the operators for NLD routes, for NLD optical fiber cabling, there we use loose tubes, and for intracity, mostly ribbon types are used. Intracity, that is the connectivity inside the cities, because there we need more number of cables, I mean the optical fiber. So that is the reason we have two types of cables. Now the next important type is the ADSS type of optical cable. Now this ADSS type also have loose tube as well as ribbon type of cable, but the main difference is wherever we need to do aerial cabling. So specifically I was talking about the FTTX network, fiber to the home network. So nowadays most of the operators are working. FTTX is a very it's growing day by day, and now everybody is taking optical fiber connectivity at their home. So this FTTX network connectivities are mostly happening in aerial cabling is happening for that, structured aerial cabling. Now to lay this cable aerially, it becomes important to change few of the features of the cable. Now in the initial two cables, let me just go back. Here you can see there is a metal coating layer also around this cable, because these cables are laid, normal ribbon and loose tube cables are laid underground. So there can be rodent, right? They can cut the cable. Now to protect from the rodents and all, we put a metal layer, which we call it ECCS tape. You can see electrolytically chrome coated steel. So it's a metal layer which protects the cable. It prevents from the different rodents and all to cut the cable. Also, with the help of this metal layer, what we can do, we can detect the optical fiber cable from top of the ground with the help of magnetic device. But that is not required in case of ADSS. Rather, we need a lighter cable, more lighter cable to handle it aerially. It does not sagging does not happens much, right? So to put these characteristics, we have designed different vendors. We have our ADSS cables. So what does ADSS means? ADSS is all dielectric self-supporting cable. So this particular cable is used for structured aerial cabling of optical fiber. By the name you can understand it has clearly two sections. First one is all dielectric, second is self-supporting. By all dielectric, it means that because aerial cabling, to do the aerial cabling, we use the electrical poles, the existing electrical poles of the different electricity boards. So there it can be, the electrical wires are there. So the engineer who installs the optical fiber cable, there should not be any fatal incident because of this metal layer. So that's why in ADSS cable, we don't put any of the metal part inside it. That's why the name indicates all dielectric. It is entirely made up of non-conducting material. And the second thing is the self-supporting. Self-supporting means that the cable, the tensile strength, certain polyethylene material is put in this outer coating layer, which maintains the tensile strength of the cable, and through this it can support by itself. So self-supporting, it does not need any other metal messenger wire to support the cable. The cable can itself support. So that's why it is self-supporting. Now this ADSS cable are mostly black and gray in color. Black are generally the loose tube types and gray are generally the ribbon types. Why these are not colored? Because to protect the cable from the ultraviolet sun ray. Okay, so that's why it is black. The outer coating of these ADSS cables are mostly black. And so there are different color codings. There are two strips you can see at the both end. So depending on the types, there can be 6F cable, 12F, 24F. So different number cable optical fibers inside these cables. So those can be indicated with different color coding of these strips. So that can vary from operator to operator. Now this is again a ADSS cable gray color, which is a ribbon type. So generally the loose tube types are black color and the ribbon types are gray color. Now the another type of cable is a figure 8 cable. Now figure 8 cable are generally two types. Here I have shown only one type. Figure 8 cable means a single cable is having two cable in it. So somewhere to lay the optical fibers, we need ROW permissions from different authorities. Somewhere, you know, to lay it again two different cables, it becomes challenging to get the ROW permissions from the different government authorities. So what we do, we lay both the cables together. So that is called figure 8 cable. You can see here in this case, I have given an example of a cable which is having both a loose tube type cable, which is 48F, and another 2288F cable. So both are together. This is a single cable which has a space to put 48 as well as 288 type of cable. And when the entire cable is laid, both the cables are laying together. So it's not two cables, it's a single cable, but both the types are laid together. It does not need a second permission from any authority. Also, you know, the installation work can be done in a single go. So it saves time. So we use this type of cable somewhere in the network. There is another type of figure 8 cable also where this 48F cable, instead of this, we put a metal support to support the cable, messenger wire we call it. That is also a figure 8 cable. So that those are few types of, I am just keeping it very brief because I need to finish it up. So these are the different types of cables which I have discussed. Now talking about the different types of SFPs and connectors. Now SFPs are the small form factor pluggable. So now what these SFPs are used to convert the electrical signal to the optical signal. So these are connected in the boards, electronic boards, and through which we connect the optical fibers. So these are used to convert the electrical signal to optical signal and transmitted through the optical fiber. Now these SFPs are made up of different vendors. Again, Cisco is a very prominent vendor for these SFPs. There is Finisar and many more vendors. Now these SFPs are generally of duplex in nature. There are bidirectional SFPs also, which transmits and receives through a single optical fiber with the help of WDM technology. Those type of SFPs are also available in the market. Now these SFPs are generally made keeping in mind a few things, that is the bandwidth required and the distance the signal needs to be transmitted. So keeping these two factors in mind, there are different types of SFPs available in market. In these labels, generally there are labelings done on top of these SFPs where the bandwidth and the distance compatibility is written. For the Cisco types, we have LX, EX, ZX, these number, you know, alphabets written, which has different meanings. Like L denotes basically 10 kilometers. That means the SFP supports 10 kilometer distance. E denotes 40 kilometers. Z denotes 80 kilometers. So whatever the requirement is, we can choose the SFP and use it. And the second alphabet, X. So X denotes 1 Gbps. There are SFPs with LR, ER, ZR. If it is R, which will denote 10 Gbps. So that's why, keeping in mind bandwidth and the distance, the SFPs are made. Okay. I'm moving a little fast. Now, the connectors, talking about the connectors, connectors are also a very important part of optical fiber network, because to connect the optical fibers, we need connectors. To connect between two optical fibers or to connect between the optical source and the detector, we need connectors, right? Now, these connectors are again of different types: single fiber connector, multi-fiber connectors. So single fiber connectors are further divided into different types based on the central member, you know, the structure. I will show you the next slide. There is a structure in the center of the connector, which is called ferrule, which is made up of some kind of ceramic material. So the diameter of that ferrule is maybe 2.5, 1.25 or some other. So 2.5 and 1.25 are the most popular type of connectors. So within 2.5 members, we have ST type connector, SC type connector, and FC type connector. ST is straight tip, then square connector, and then fast connector. And then in 1.25 ferrule type, we have LC type connector, which is the most popular in these days. Okay, I'll show you the images in my next slide. Then MU and different, I'm not talking about all other, only the popular ones. See, the multi-fiber connectors are not so much popular, which are mostly used in some special sectors. But in telecom industry, we mostly use single fiber connector. And among these LC type connectors are the most common, which are used in the, also SC/ST is also used. So these are few images of the connectors you can see. ST type connector, the left side ST type, it is the straight type connector. And then the now these connectors are different when it gets connected, it has different mechanism. Like the straight tip connector, it uses bayonet type of lock to lock with the adapter, and the SC type square connector uses push-pull method to connect with the adapter. Then we have FC, which uses the screws to get tight. And then the LC type, you can see it has a locking mechanism in this way, push and it gets locked. So that is the most popular. Now there are different color codes also for the connectors. So the most popular type of color codes are gray, blue, and green. So these gray denotes multi-mode type of fiber supports. This type of connector supports multi-mode fiber, and blue denotes blue denotes the. Now it comes another topic is the ferrule type. So it is a straight type of ferrule, angular ferrule. So if it is a straight type of ferrule, that is the PC type of ferrule, then that is blue color. Blue color indicates that the ferrule is straight type. Then the green type is the angular PC. APC, we call it LC APC. Okay. Now angular type is mostly used in the NLD or long distance communication because the return loss through this type of ferrule is lost. So I'll talk about the ferrule also a little bit. These are the different ferrule types in the connectors. So the first one is flat, PC, UPC, and APC. So in the flat PC and UPC, the loss is more because of the reflection you can see in the left side image, bottom left side. But in the APC type of ferrule, the loss is less because the reflected ray gets dissipated in the cladding layer, right? So that's why the loss is less. So APC type of ferrule type connectors are mostly used for long distance communication. Here is a picture of LC APC type of connector at the right hand side. The green color denotes the APC type of ferrule. Now the next section is fiber laying technique. So while laying the optical fiber cable, we have different techniques. It can be underground or aerial. So underground techniques include open trenching, micro trenching, molding. These are the three, and HDD as well. These are the four technologies which are used to lay the optical fiber cable underground. Okay, so the first one is open trenching. This is mostly used in the NLD type of optical fiber network, where the fiber cables are, this type of trenches are digged. These are manually digged with the laborers alongside the roads. Suppose the state highway, a national highway, beside that parallel to the road, we dig such kind of trenches. The depth and all the width of these trenches vary depending on whether it is a NLD type of route or an intracity type of route, or depending on the location, the strata of the soil. It varies depending on different factors. I will not go into that much depth about the specification of the depth and all. Just talking about the different types of fiber laying technique. So this is the open trenching, inside which we lay the ducts, and inside the ducts, we blow the optical fiber cables. So this is open trenching technique. Next comes the molding. Now, let me just 1 minute in this slide. For open trenching, we rigorously need ROW permissions from different authorities. Also, we need a very clean route to dig such kind of trenches. Now, it may not be possible in places. There may be obstacles coming in front. Also, it becomes hard to get the ROW permission, the right to work permission, right of work, we say. So it becomes hard. At that time, we use manual, boring technique, which we also call molding technique. So this in this process, what we do, we dig pits in certain distances, and then those two pits are connected underground through this kind of trenches. Okay, this kind of long haul trenches we dig, and through which we blow the optical fiber, just like the the rats or the moles digs the tunnels underground. Similar way, that is the that is why it is also called molding. Okay. Next comes the HDD technology. This is a very effective fiber laying technique and is widely used in case of intracity intracity fiber laying. So this uses this kind of machinery, you can see, which is very costly but very effective and very fast. So what it does, it drills inside the soil at certain angle, and what it does, it drills through, and it is monitored by a person sitting here, which can direct this drill inside the soil. Another person travels through this entire way and gives in the information with the help of a magnetic device. He goes and he detects the cable, and he gives the information to the another person who is sitting here, and accordingly he drives that the drill bit under the soil, and finally it comes up from the other side. So this we use generally in the places where we need to cross highway or a big water body is coming. So there we use this kind of technology, HDD, horizontal directional drilling, and it comes up from the other side. So this is a two-way process. So this is a two-way process. In one way, it digs the tunnel and comes from the other side, and while returning back, what it does, it connects the duct at the tip of the drill, and it pulls the duct through that tunnel, and in the same time the duct also gets laid. So the time saves. In the same way, while moving forward, it digs the drill, while coming back it lays the ducts. So it's a two-way process. That is the reason it is very fast and effective and widely used in intracity fiber optic cable laying. Okay. Now another important underground cable system is micro trenching. This is also used in the metro cities, in very important roads where we need to lay fiber cables through the roads there, but we don't have much mud space beside the road to dig such big trenches with such depth and all. So there we use this micro trenching process, which uses a blade cutter type of, you can see the machine, so which cuts a very narrow trench is done with the help of this machine. The width of this trenches approximately it is about 50 millimeter or so. So that kind of trenches, and inside which we place the duct vertically. In case of open trenching, we place the ducts horizontally, but in case of micro trenching, we place the ducts vertically on top of each other in this way, right? And that way it saves the space. So this is used in the metro cities mostly. And after that, it is covered with concrete, PCC cement. It is covered. In this way, the ducts are laid, you can see, vertically on top of each other. And then it is covered with PCC to make a level with the road surface. Next, and the last cable laying technique is the aerial cable laying technique. This is also widely used inside the cities where we don't get much permission to lay cables underground. We don't get ROW permissions to dig trenches inside the city. There we use the existing structures like electrical poles or any poles, or maybe building walls, such kind of structures, or pillars. We use those structures to lay cable aerially, not underground, over the ground, right? So it is a aerial cabling. You can see it uses different accessories to do this structured cabling. I'm not going into depth about what are the accessories and all, but just trying to show you the different methods of cable laying. Okay, my last part of today's topic, it becomes important to talk about the different equipments we use to maintain and manage the optical fiber network, because with the invention of these equipments only, the optical fiber has grown its importance, because it can be managed very easily with the help of these equipments. So few of the important equipments I will talk about. First one is the splicing. It is very important. Very often optical fiber gets cut, okay, maybe due to different maybe the roads are under process or any other thing, so it gets cut very easily, or rodent may cut or something. So splicing is a mechanism to join two optical fibers wherever there is a fiber cut. Not only in case of fiber cut, optical fibers generally comes in drums, okay? So 4 kilometer or 2 kilometer drums of optical fiber cable. So if we are doing a fiber network of maybe 50 kilometers, so we have to join the drums in between. So there also we have to splice the optical fiber with the help of this kind of splicing machines. So there are different splicing machines for loose tube optical fiber as well as ribbon type optical fiber. So they are different, okay? And there are two types of splicing machines, techniques. One is mechanical splicing, another is fusion splicing. So mechanical splicing, after the fiber gets spliced, the losses are remains. Little more loss happens, but in case of fusion splicing, the losses are very less and very effective. So in fusion splicing, what it does, with the help of heat, it melts the end of the optical fiber and joins the optical fiber. So this is the splicing machine. You can see the middle chamber here, the splicing happens with the help of a fusion. Now the next type of equipment is this one, okay, connector inspection. So this is required to maintain, to check the optical fiber network, the adapters and the connectors, because dust is a great enemy of optical fiber communication. So in order to check how much of dust is accumulated or in the adapters or the connectors, we need to check with this kind of inspection microscopes, which you can see the image at the right side. We can put this. This is nothing but it is capturing the image with the help of lens and all. It has different focus control and zoom control buttons are there. And finally, it can be this USB end can be connected to a monitor or a OTDR monitor also, where we can see the image that how much of dust has been accumulated on the adapters and the connectors. So by looking into that, the engineers, the maintenance engineers can go ahead to clean the adapters and the connectors with the help of different cleaning tools available, right? So next is the OTDR. This is a very, very important instrument which is widely used in fiber optics maintenance. So this is optical time domain reflectometer, OTDR. So what it does, it detects if there is any fiber cut. So at what distance the cut is there, what is the end of the fiber, means how much length of the fiber. All these things are detected with the help of OTDR. Now what is the mechanism? It sends a pulse of light through one end of the fiber, and in this screen it shows a graphical representation. Wherever there is a loss or an event in the optical fiber path, it shows a peak in the graph. So that will show that there is an event in the path, right? With the help of such graphical representation, engineers can easily understand that at certain distance there is an event, there is a loss happening, maybe due to a maybe the fiber has got compressed, or maybe it has got bent, or maybe there is a cut, there is a fiber cut. So all these things they can detect, and they can reach that particular distance and can act on it. They have to splice or whatever, they can act on it and make it okay. So this is a very handy and useful instrument in order to maintain optical fiber network. So this is the last thing, that is LSPM, laser source power meter. Now this is basically two devices which is used to check the health of the optical fiber. So one of the device, we connect two end of the optical fiber in both of the devices. From one of the devices, we inject a source of laser or LED, laser light. So that is the laser source, we call it. Another is the power meter. So that laser source is injected, and the another device detects that laser source. Now, while doing this process, the power of the light is measured in the screen and displayed on the screen while injecting and while receiving at both the end. Now, difference of this power will give you the loss through the entire path of the optical fiber. So that is how we can understand if that loss is within our link budget. If that is the intended loss or less than the link budget, then we will consider that the path is okay, in okay condition. Otherwise, we have to check and work on it. Something wrong. If suppose the amount of loss is more, then we have to see, maybe there are dust accumulations, or maybe there can be several reasons. There can be bends in between, there can be fiber may get compressed somewhere. So we have to inspect and make it okay. So this is how laser source power meter. Now, while this measuring this, we have to understand one thing, that the couplers and the patch cords which are used to connect the actual fiber path, those are also contributing to the amount of loss that is shown on the screen. So we have to take that reference reading initially, and we have to subtract that. We have to from the actual loss happening. Then only we will get the actual loss that is happening through the fiber route. Okay. So first we have to do reference measurement, and then we have that amount of, suppose the reference measurement here in the example given is minus 7.2 dBm. And finally, when we do in the actual fiber path, it is showing minus 21.8 dBm. So we have to subtract this 7.2 dBm from this, and finally the amount is minus 29.0 dBm. So that gives the actual loss through the fiber route. Okay, so that is how we need to use this LSPM device. So with this, my presentation ends, and that is all I want to discuss today. Now, I'm done with all the topics. Thank you very much. Over to you, sir.
Thank you, Abhijit, for your beautiful presentation. May I request Devamoy to start his presentation? And for all the audience, at the end of the Devamoy's presentation, we will take up the question and answer session. And you can meanwhile write your questions on the Q&A so that we can take up. Devamoy, please.
Good evening, sirs. I am very much pleased to deliver my presentation here, and I feel very much privileged to join this session. This is a technological session, so I must not waste any time by giving welcome sessions, welcome addresses on all these things. Let me start with the discussions. Actually, today,
Abhijit, close the session first. We can still see the OBG screen.
Okay, so
you can just stop sharing screen.
Yeah, I'm trying to do, sir, actually.
I think you have to press it once again, sharing screen.
I think if
Okay.
sir can share, then this will be
Okay.
override.
Devamay, please try. Because all panelists can share.
No, sir. Actually, while I am going to share, this is showing that you cannot share while other participants is sharing. I think
Yeah.
Mr. Abhijit should try to
Close it.
close it.
Okay.
So please press share screen again.
Please share screen again, it will go.
I don't know why it is not going.
Okay, let me try stopping.
Maybe if I can leave and join once again, this will.
Mhm.
It is now showing my screen. Devamay, can you try now?
Yes, sir. Yes, sir. No, sir. You cannot start screen sharing while other participant is sharing. No,
New
I
share?
can't.
You cannot. Pause share. No.
Yes, yes.
We are learning. This is the first time I am working as a host. So thank you. Please
Thank you, sir.
continue.
Sir, actually, today my topic is to continue.
We are not. Hello. We are not getting your slides.
Yes, sir. I am starting.
Yeah, but slides. You present the slides. I'm not getting your slides.
Yes, sir. Yes, sir.
You have to share it.
Is it visible, sir?
No, I didn't get it.
Your presentation is open, no? On your laptop?
Yes,
And
sir.
then you can just share screen. Then it will automatically share.
Yes.
Now it has come.
Yeah.
Now you can go to presentation mode. Fantastic. Okay,
Yes, sir.
please start.
Today, what Abhijit host has told just now about the optical fibers. Basically, the constitution of optical fibers has been presented here, and I am to continue with the equipments and systems and technology to use these optical fibers in our network. Basically, optical fiber can be compared with the highways built in metros and cities and all these things. But the equipments and the technology can be compared with the management systems to control the traffic over the highways and medium. In optical fiber systems, the optical fiber has got enormous bandwidth. But to use this bandwidth successfully, we need some technology and equipments, and also we need some control systems so that we can use it successfully in our network. Let me start. My points to discuss today are the technological evolutions of telecommunications. Next, I will discuss about the PDH and SDH systems. Then I will go to WDM technology and then CPAN under the platform of MPLS-TP, and finally I will end my session with optical transport network. As we know, tremendous need of bandwidth is here. We have been developed with the mobile technology. Now people are running after transferring higher bandwidths. We need to see very faster. We do not want to waste our time, and also in our every field this bandwidth transmission is very necessary, and here the evolution comes with the requirement of bandwidth. In 1940s, when we use only telephone as a landline, and at some instances we use telegraphs also. That was our need for transmission and telecommunication only, and not much more than that. But after some time, in 1940 to 1980, there is not much development in telecommunication. At that time, the need for this bandwidth was not so much high. But when the time has come in late 90s, we see that mobile growth started, computer age started. We use graphical user interfaces, and as this the growth started, we need to transport more and more bandwidth through this optical fiber medium. Optical fiber is nothing but a guide, a wave guide, which can guide bandwidth. Actually, bandwidth, in terms of bandwidth, whenever we speak, let me explain some in a very simple way. A bandwidth is nothing but the signal which is composed of different frequencies. The more the bandwidth we can transfer, the more the frequencies and more the intelligences from one point to another. Let me explain it very clearly, that whenever Lata Mangeshkar sings, she has got very rich number of frequencies, so that this her voice is very melodious. But if our medium cannot transmit all the frequencies all together, then the song cannot be sound very nice. And that is why now we need this high definition transmission. This high definition transmission requires high bandwidth transmission, and high definition transmission, if you know, it's a very high quality of audio and also video. So the more the high definition, the more the bandwidth requirement. So I think I can give the next slide. This, according to the need of people's demand, from telephone to mobile and from our normal life to computers, I can see that our technological growth started. During 1940s, there was very simple technology to transfer this bandwidth from one point to another, point to point, copper line only. There was not much networking business. Now, in 1980s and 90s, this PDS technology was evolved. It is because of the need of our user level interface. User level interfaces means telephone, computers, then mobiles, then now our business and all the field. We need this networking. We need to transfer our bandwidth. So first level is started with PDH, when we could transfer only 2 Mbps signal. Actually, 2 megabits per signal can carry a very small bandwidth in respect to now what is transferred up to 800 Gbps, 800 gigabits per second. And we can imagine, we can see this graph that we started E1, that means 2 megabits per second, and the graph rose to the second milestone. This is the age 1995 and 2000. During this age, we used SDH system, and in which we could transfer maximum 10 Gbps, 10 gigabits per second of bandwidth. Now let me state, bandwidth is a quantity, 10 gigabytes, and whenever it is in terms of rate, it is Gbps. That means 10 bits per second. It is the rate of for transmission. Next level, at the end of 2000 and 2000, between 2000 and 2010, we started using DWDMs. DWDM stands for transfer enormous bandwidth, and the level of say 100 Gbps. And then in the milestone 4, when digital cross connect DXC came into the network, at that time this control system was very effective to transfer our this data from one point to another without giving much loss of time and latency. And finally we came just this age where OTN is being used, optical transport network, where all the capacities and all the systems can be put together and transferred from one point to another point. And also we can handle a complex nature of networking in this present scenario, where business and all the offices are connected through internet. With a clumsy internet, this handling is very difficult. So this handling of this data can be managed by these systems. Our future is SDN, that is software dependent network. Till now, what we did, our network based on the optical technology, we used to have human interventions at some points, but we are looking forward for software dependent networking, when human intervention will be very less. Some point will be fixed with without human interventions, and automatically these softwares will switch the data from one point to another point if there is some cut in one regular path. Now, as per the demand of this technology, transport architecture is also changed with the basis of time. Now, let me remind that OSPF model, where the first layer is physical layer, we use optical layer, and then we use this transport layer, then the service layer. Optical layer means this optical fiber just now, which Ghosh has told us. And next comes the technology layer, that is I am going to discuss, and I'm discussing this one. And service layer is nothing but the services we want to transfer through this transport layer and optical fiber medium. Now, you can see that during 1995, also Mr. Ghosh has told that now the 1550 nanometer band is being used because of less attenuation and also very good high bandwidth also. We can transmit high bandwidth through this lambda. Now, in the first 1995, we used SDH as a transport layer, and in that transport layer, services were imposed, PDH and IP and ATMs. IP means some IP-based services, that is computers and other networking elements. In 2000, we started using WDM technology, wavelength division multiplexing. I am coming to this technology later in details, but till now I can show you that this optical fiber communication is helped much with the WDM technology to transfer more bandwidth from one point to another. In this 2000, this transport part is only SDH, and our service part was PDH and IP based. In later years, when this our mobile technology started, and through mobile we started using internet. You can remind that the GPRS internet was started with 2G technology. Under this services, we started using SDH with Ethernet. So Ethernet on SDH was then developed. SDH was not supposed to transfer Ethernet bands, but later some technology was imposed to transmit Ethernet and IP systems through SDH network. And with this, during this also, this framing technology was started with FEC, forward error correction. This has got a very faster transmission technique. Now, after 2005, we started using DWDMs and DXCs and all these things. Now, 2010 onwards, OTN has been used in worldwide network, but in India, OTN started a bit late. In India, it is maybe in 2018, we started OTN very widely. Now it is in full-fledged in our network. OTN has got all the services in one platform. That is the beauty of OTN, and I will discuss in detail later on. And in this optical fiber medium, that is physical medium, this WDM and ROADM. WDM is wavelength division multiplexing, and ROADM is reconfigurable optical add drop multiplexing. In those two technologies enhanced the capacity of optical fibers. Let me discuss about PDH. PDH is actually very used for low bandwidth transmission, and also in terms of today's bandwidth transmission aspect. When we talk about GBPS, 10 GBPS, 1000 GBPS. So SDH is also going to be obsolete in terms of bandwidth transmission, but still it is being used in our network, because in actual case, when actual data is to be transmitted from one point to another, if we are not going to transmit videos and high definition videos and channels, then for transmission of data, this 2 Mbps or 4 Mbps or 80 Mbps is sufficient from network point of view. So still this 2 Mbps and 150 Mbps in SDH is still being used by your networks for connecting networks of banks, particularly ATMs, and in our regular uses also 2 Mbps bandwidth is sufficient for normal telephone lines and normal usage. Actually, PDH and SDH has got developed some problems with the network. Let me discuss about this PDH system. PDH has got step-by-step multiplexing. As you know, to transmit higher bandwidths, that means we need to pump different signals into one medium, and different signals mean different services. So here are the different services. PSTN is public switch telephone network. That means the basic telephones which were used in the before 2000 widely, still it is being used, but in a very less number. That is landline telephone. ISDN is a very widely used networking technology for banks and all. This integrated services digital network, where this telephone and our internal networking was combined in one network. Though all this required very less bandwidth, ISDN was limited to only 2 Mbps. PSTN required for each channel only 64 kbps. Or GSM is landline. At that time, the landline, that means, GSM means our mobile technology. It required only 2 Mbps or maximum 6 Mbps at the beginning, when 2G services were given. And final internet, think of the internet era of 2000. At that time, we used to connect Yahoo, and maximum we could see our mails. We can check mails. We could not think of transferring a video or audio through emails. We could only log in and download our data to the mails and all these things. And also, if you can imagine, with a button of click, we had to wait some time. Sometime means it may be 1 minute or 2 minutes to open the window. So that was the condition of internet, where only say for 2 Mbps or 4 Mbps speed was there for the overall bandwidth. So all these services were being used in the PDH technology. Now, step-by-step modulation is multiplexing is that. So this 2 Mbps are multiplexed into 4 Mbps and 8 Mbps. 4 into 2, that means 4 to 8. Now, this 4 8 Mbps are then multiplexed to 34 Mbps, 434 multiplexed to 140, and finally we could transmit from this point to this point a 140 Mbps signal. That much was the bandwidth transmission from one optical fiber media. Let me try the analogy. What now transmitted, it is 800 Gbps, 800 Gbps and 140 Mbps. This is megabits per second, and now 800 Gbps. It is much more bandwidth which is now being transmitted. And this PDH technology was only linear technology. That means only point to point. When network is now built, it is a point to multipoint or maybe a mesh network. So the data from one to another point by different nodes within the network. That was the network building, but that was not possible at the time of PDH. It was possible, but it was then became very clumsy and very difficult situation, and management was not possible. So PDH was discarded. Then this SDH came into the picture. SDH has got a marvelous achievement for giving this ring structure. In this ring structure, we could transfer this 140 to 10 Gbps. STM16 is basically 2.5, but later we developed a system of 64 Gbps signal transmission, where basically 10 Gbps signals can be transmitted through the ring medium. In this also, we can get some management function, so that from one point to another, when transferring, say from this point to this point, we are transmitting some data via this medium. Now, if this point, there is some cut here, in the ring fashion, we could transmit from this point to this point automatically. So this automatic switching was developed in the SDH. That was the development from PDH to SDH. Later on, this SDH also become obsolete, because now we need to transmit this data very authentically and successfully and with high bandwidth. So this was not possible in SDA. And also there is another very much drawback with the SDA system. This is called synchronized digital hierarchy, where all the nodes are synchronized, are to be synchronized with the clocks, with the different clocks. So this synchronization was a big challenge for SDA to maintain this network in SDA. So we discarded this SDA systems also. Then after this PDH and SDH development, we started to have wavelength division multiplexing to get more bandwidth transmission. We need to develop our technology in wavelength division multiplexing. In wavelength division multiplexing, actually, what happens? Our optical fiber, whenever it is laid from one point to another point, it gets either breakages or damaged in some parts. It cannot transmit point to point without technological development. That means the losses are more and more day by day. So it becomes unusable. But this wavelength division technology can be utilized to get errored or more lossy fibers successfully in our network. In this technology, what happens? Signals of different lambda, that is, say, it is basically our transferred to prism technology, where one light can be segregated into colors by using different wavelengths. Now, in one wavelength, we can transmit from one point to another point. We can transmit another signal in another wavelength to the single fiber. The same fiber is being used where the wavelength division is there. So as per the color, the wavelength is divided, and we can use this optical fiber with a very efficient manner with a high bandwidth transmission. This point is called multiplexer, where ingress of our signals are there, and in the other end of the network where the signal is transferred, it is called egress, where the signal is demultiplexed. The similar fashion is achieved in case of other sections. In WDM, wavelength division multiplexing, we can have two types of WDM technology. One is coarse wavelength division multiplexing, another is dense wavelength division multiplexing. In coarse wavelength division multiplexing, we have got channel spacing of 2T nanometers only, and that is why it is called coarse. We can use very less number of channels, say 8, in one DWDM fiber. In case of in CWDM fiber, in case of DWDM, we can have maximum 88 channels in one fiber. That means we can divide this lambda into 88 parts by using a channel spacing of 0.8 nanometers. So here is the difference between two systems of WDM. Wavelengths can be divided into coarser and another is denser. This denser type is used in metro networks, and coarser type may be used in our access network. But this DWDM, that means denser WDM technology, is being widely used in our all over networks. Recently, we have developed WDM technology that can use 800 Gbps transmission from one point to another. Here is the basic of WDM transmission. From DWDM transmitter, this different lambda are there as per the multiplexing. There are maybe 8 lambda as per the equipment configuration. We can have 8 lambda DWDM, then 12 lambda DWDM, and then 32 lambda DWDM, and 40 channel DWDM also we are having, and also we can have 80 channel DWDM. Now, as per the requirement, we use these lambdas as per the requirement of our network, as per the design of our network, as per the demand of transmission of bandwidths. So, depending upon this, we use the selection of channels. So, in optical marks, these channels are multiplexed into one fiber, and in this optical fiber, what happens, as I mentioned earlier, to use this optical fiber medium in a better way, we need to pump this signal, this channeled signal, to some higher dB. That means we have to give some more power so that it can transmit from one point to another point. Say it can traverse kilometers, 100 kilometers, 100 kilometers, or 40 kilometers, or 80 kilometers, depending upon the stretch of our network. So as per our requirement, we need to pump this signal to some higher band, and this OLA is used to this pumping. What? Optical line amplifier. Previously, now I can mention here that previously we used the same thing to transfer this signal from one point to another by using regenerators in different points, where this 4R technology was used, reshaping, regenerating, and all these things. But in that case, in previous DWDM technology also, we used optical to electrical, then again from electrical to optical signal, so that this signal can be made to, it can be given some higher band. But now this OLA technology, this optical line amplifier technology, can give this input to getting higher side by using optical fiber line amplifier. This is another diagram where this inline amplifier is being used. In the previous slide, we can see that this amplifier was used here also, and in this diagram we can see that this is used in between our transmission to get this signal amplified in as per the need of distance of the network. Then the second, now let me give some idea about the amplifier. That means RBM doped fiber amplifier, which is a rare earth element. RBM has a very rare kind of capacity. When this optical source of say 1500 nanometer range is pumped to this EDFA, EDFA gets excited, and this EDFA ions goes to some higher state, and this higher state, it stays there for some very short period, and that say for 1 millisecond, and that period again it comes to some metastable state, and during this coming, some energy, it leaves some energy, and that energy is given to this optical ions, and optical source gets at more power. See how our optical signals are here with this much power or having, and then after EDFA we can have more power of our optical signals. That means these are the different lambdas. Say these are the colored lambda. They say red, green, blue, and this orange. This became so much bandwidth gain. So this is the beauty of EDFA amplifier and direct amplification of our fibers very easily, and that is the development of our DWDM systems in 2000 onwards. In WDM, we have got some different technologies. It is in previous slides I showed you this line technology only from one point to another. Here, one point, while going from one point to another point, there we can drop our signals. Here is one client point, here is another client point, but in between, if we want to drop another client point, this can be possible by using OADM. This OADM is optical add drop multiplexer. It is similar to our previous add drop multiplexers, where we can drop our signals as per our requirement. In this case, this transponder systems are there. This OEO function has been shown. In case of if we use EDFA, then this OEO functions not needed. Now, these optical transponders are used here to get this client signals in through this OEO. We can go to the MUX and DMUX combined here. For both way transmission, we need this MUX DMUX combined equipment, and then again this EDFA function, as I described earlier, it comes with the these are the different signals are fed to MUX multiplexers, and two signals, red signal and blue signals, are mapped to different lambda of the same optical fiber. Here you can see this is one optical fiber input for one client signal. This is another optical fiber input for the another client signal, and when it is MUX, it goes to one optical fiber only. This is one optical fiber only, where these two signals are spaced by wavelength division multiplexing. So these signals are here, but these signals are having this much power only. Now, after EDFA, this power is pumped to this one. Let me give some idea about the power. This is dBm power. Actually, we can can have this dB as the reference level. We can gain up to 30 dB by using EDFA, and this after this EDFA, when it is going to the main route, the power output is at the level of plus 17 to 18 dBm. So this is very easier to transmit from one point to another, even if this fiber is having some error due to its basic loss in the route in some point. Now, this OADM can be used to drop this signal in somewhere here. Say here this red signal and blue signal are coming. It can be passed from this point to this point. But if we need this red signal to drop here, we can drop it by using this OADM function. So this is what about I'm sorry, I have to start it from the beginning. I have missed it some point. Yeah, it is the RODM function. I have to give some discussion about the RODM function also. RODM is reconfigurable optical add drop multiplexer. As in case of OADM, optical add drop multiplexer, this optical signal, when it is input and it is going from one point to another point, it is add drop function, but in RODM it can be reconfigurable. That means we can use it, we can drop it, we can add it also from one point. In another point, we can use it as a add drop function also. This is WSS, that is wavelength selective switch, where this wavelengths can be selected, and switching function is included here. In the earlier slides, what I have seen, that one wavelength, one wavelength in earlier side, let me go. This one wavelength, that is red wavelength, is going into this optical fiber, and another wavelength, that is red wavelength, is going into the same optical fiber. Two wavelengths are going side by side, and here also red is going and there red is going. Here the difference is that if we can change the wavelength from one point to another by switching. Here this red, yellow and green wavelengths are there, but at this point this red wavelength is mapped to blue wavelength. This point, this is the add drop point, this third point. Here A point, this is B point, and here is the C point. And the third point is there, where we can drop our wavelength as per our requirement. As we drop this and cannot second, so we have map this or this switch this red wavelength to some blue violet wavelength, and a similar fashion this orange wavelength is mapped to violet and green wavelength is given some other color. So this is the function of reconfigurable optical add drop multiplexer. So this switching function is very much requirement to make our network successful. Next, I must start with our discussion about CPAN technology. CPAN basically is a network which can accommodate different services in the same layer. You can see that these are the services, different types of services are being used in this network. And this MPLS TP is the packet transmission technology. Now, let me give some idea about packet transmission. Previously, when in PDH and SDH, we used circuit transmission, and at that time, the real-time transmission was there. And in MPLS TP, we started using packet transmission. Packets are delivered from one point to another. We made our signal into packets and given some packet numbers. That is the beauty of this MPLS TP technology. For transmitting from one point to another point, these packets with the numbers are transmitted, and this packet transmission technology is being used widely for covering all the networks altogether. Here you can see from one point there is an access network. This is called the access network, where our main data is fed. Some banks may be there, some houses may be there, some business houses may be there. Here you can see this is the residential complex. We have some residential network. Residential network means it may be a PON network which are using GPON, that means FTTH connections are given in this network. And in this business corporate houses, that means banks or other business areas where this business are run by networking. This business corporate house can have its own network. And then again, another residential network is there. So these are the different networks are mapped into access part. So this access part is having some MPLS TP network. And again, this access part actually again is connected with the another MPLS TP network. This is MPLS TP aggregation network. This is the greater network with having greater bandwidth equipments. And again, this is again another one is edge part. Edge part is where this transfer of data is being taken place through the routers. The routers are used as per the need to transfer our data from one point. Let me explain. Suppose bank at Calcutta, we need to transmit this. We need to transfer this data of Calcutta bank to Delhi bank. Now, to transmit from Calcutta, we have to connect this to our local part. Say in Calcutta, we are connecting this area. This network is connected to our metro network. Again, metro network is connected to this edge network, which is having our Delhi and Calcutta both connected. So this router part is coming into picture where Delhi and Calcutta is connected. Now, after this multi-service provisioning platform, it is going to, it may be use this network if it is some video or TV net services. But in case of our case, for transmission of our bank network, I have to travel this path. We will use this core network. By using this core network, we'll reach another access part at Delhi, and finally we can travel from Calcutta to Delhi by using this network. And the beauty of this network is that this is in one platform. This was not the case in previous era, where this part all are segregated. Different parts are segregated. This part, access part, was basically maintained by Calcutta, and this part was also maintained by Calcutta. This is access Calcutta part. This is also metro part, and this was the core network part where Kolkata, Calcutta, Delhi, Chennai, and all these things are there. And similar access part was there with this, connected with this metro network.
Devamoy, already
Yes,
we are late by 12 minutes. Can you please finish
sorry.
quickly? Thank you. No problem. Just,
Sir, I'm
no, it's very interesting. You know, you're listening very attentively, but senior people are there.
I'm just going very short.
Sorry.
However, as we have reached our time, I have to finish it very fast. Actually, it was basically very difficult to conclude all these things in such a small time. It is my fault that I could have get some shorter slides.
No,
So
it's very interesting presentation. We are really enjoying your presentation.
Okay, sir. Thank you, sir.
Don't take it to that.
No, sir. Thank you, sir. Now, this actually I am finishing it. MPLS technology. It is very wide. I am just going to optical transport network, where the same thing is happening. This optical transport network, but in a bigger way. It is actually optical transport is a network, is the physical thing, and MPLS TP is the technology behind this physical. So I just tried to give some idea about the MPLS TP network. Now, this optical transport platform is this platform to give the same different components in same platform. That means transportation, multiplexing, routing, management, supervision, surveyability, and all these things can be used to the same yeah, platform. Here we can see that this is the OTN client signal, where all the signals, SDH, IP, ATM, all these signals can be fed and transferred from one metro network to another core network, then another metro network, and this networks can be added. And the beauty is that if we can, if we monitor our client signal at this point, we can monitor this at this point also. This is called path monitoring. This path monitoring helps to pass our signal from this point to this point. Say it may be this metro network, as I told you, it may be a Kolkata. Then it is core network might have different cities. It may be Bangalore, it may be Chennai. Here it may be New Delhi, and all these things. All the cities are there. Then again, it is going to some other metros. So if there is some cut, it can be routed in different path with very easily, and the system will do this. No human intervention is required. So this is the beauty of OTN platform, where system will do this, that I mentioned while trying to start with the slides, that SDN is our future. So system dependent network can be achieved by using this OTN. Here some OTN client points are there. I am skipping. This is very details. It is not required for day-to-day use. I am skipping it. These are some OTN diagrams. OTN lines are used where different transport units are there. Depending upon the use of equipment, we need to transmit our signals in different sections. Say 1.2G as 1G Bps bandwidth, up to 100 Gbps bandwidth can be transmitted here in different points. So from this point, we can feed this is our user interfaces, where user can feed their data as per their requirement. STM, it can be STM, it can be STM64, it can be 100G, and transmitted to 100G signal. And also this OTN is basically this WDM function is used here in OTN also. This is a layered OM function. I must finish it by this layered OTOM function. These are the three layers: the management layer, transport layer, and control layer. Management layer is the it may be human dependent or system intervention. This switching can be done from one point to another. Here also this switching is shown. If this is cut, this is the normal path. This is the normal path where this service is going. If there is a cut, then it is taking the second path, and if the second path is cut, then the third path is taken, and this way we can have a number of paths to transmit our signal without failure. Again, this is dynamic restoration. This is as I explained previously, this same path, same way, this signals can be restored by using this dynamic path, and this total switching time is only 50 milliseconds, that we cannot get much of our bandwidth loss. That means whenever we can view our video, or we can listen some music, we will never feel that there is some disturbances in our network. So that's all from my point, and I'm very much sorry that I took more time, and that's all, sir.
Thank you, Devamoy. Not only sorry, we're very much happy that you spend so much time with us. It's a very interesting session. You can till now we have 32 participants. We're waiting in the Friday evening listening to you.
Yes, sir. I started with 45 participants.
Yeah. Then now, okay, some of them have to go. Now I think we have take few minutes to the question answer. Let me read out the questions. First questions, I think somebody from Anonymous, they said, each PPT will be provided to participant. I think that Institute of Engineers will decide on that. We'll share our PPTs with Institute of Engineers and they will take a decision as per protocol. I don't know exactly. Now, what is the cost of per meter length? I believe it must be optical fiber. I think somewhere Obijit mentioned that is price of same almost in copper cable. So that way. And one another comment is slide not available. I do not know exactly what institute does with the slides, but institute may get back to you, or you can also check with institutes. What are the other questions? I don't see any other questions there. So what I'll request now, Professor Nitosh Kumar Brahmo, Honorary Secretary, West Bengal State Center Institute of Engineers, to propose formal vote of thanks. Over to you, Professor.
Thank you, Engineer Ram Chandra. I am very overwhelmed hearing the lectures regarding the today's topic, optical fibers in the transmission. Is really wonderful. But I will request you especially to start such type of lecture. You have to shift the time towards 4 o'clock or 5 o'clock, not in 6 o'clock, because it will not be completed within 2 hours. It is so vast and the gigantic concepts today in the digital technology, where our Prime Minister is very proud that we are moving to digital technology. Yes, well, but the thing is that when I hear this basic concept of the lambda, then I have to go back to our basic energy concept of Einstein, E is equal to mc square. At the same time, Max Planck, where the E is equal to, he said, the C divided by lambda. So lambda is one of the most new frequency. See, energy is equal to new lambda, and where lambda is also be now used as an engineering concept of optical fiber, where the length and the transmission is being defined with the wavelength, and the wavelength capacity is being managed by the wavelength of the light, and that's a wonderful. But with that, I have to then conclude my personal, what you can say, duty to give the word of thanks to everyone who were present in this evening. Let's say in that way, it is my proud privilege to extend my sincere thanks and gratitude to all the distinguished participants. The technical webinar on the theme optical fiber communication, organized by Electronics and Telecommunication Engineering Divisions of the West Bengal State Center IEI through online platform Zoom. At the outset, I convey my sincere thanks to the panelists, Mr. Obijit Ghosh, State Training Local Training Lead, Reliance Geo Information Limited, West Bengal, Mr. Debomoy Bhattacharya, Divisional Manager, BSNL, on today's technical webinar, who have very nicely delivered their lecture. My sincere thanks also goes to my colleague, Mr. Sandeep Kumar Dev, Chairman, West Bengal State Center, IEI, our beloved President, IEI, and I will say Narendra Singh, Professor Dr. Tara Singh Kamal, Chairman, Electronics and Telecommunication Engineering Division, Board, IEI, Professor Dr. Shapun Bhomi, Chairman, Kate, IEI. My heartiest thanks also goes to Sri Ramachandra Chakravarti, Convener, Electronics and Telecommunication Engineering Division Subcommittee, West Bengal State Center, IEI. As moderator of the today's program, I convey my sincere thanks to all members of the Council Division, members of Electronics Telecommunication Division Board, all members of the Committee West Bengal State Center, IEI, all members of Electronics and Telecommunication Engineering Subdivision, Divisional Subcommittee, West Bengal State Center, IEI, Director Technical and his team of IEI for their wholehearted support to make the program a great success. Last but not the least, my heartfelt thanks goes to all who were behind the screen to make the today's technical webinar a success. Thank you once again. Good evening or good night, whatever it might be. From my side, I convey everybody that really we are very happy to hear this webinar. Hello, can you hear me?
Yeah,
Thank you, Professor.
Have you heard
We
my?
are closing. Yes, we can. We are closing this
you, sir.
session for this evening, and let's wait for the interesting session in December. I
Yes,
think we will be
but kindly shift the time to 4 o'clock. Otherwise,
it will be difficult,
yeah,
sir, because all of us are working.
my
And
sincere-
Devamallu has come from his office. I have come from my office. Chanchal has come from my office. Obijit has come from his
Exactly.
office.
In your
For
side,
office, till
thinking
6
in
o'clock,
that
we have
way,
to have the office.
I have to think also in my way that the members who are all present in the office, they are really getting little bit annoyed to go back to home because
Yes, no, they are sitting at home only. I think home of the everybody's.
yes. So now please consider also these people. They
Okay, then I definitely, definitely, sir, definitely.
yeah. Please.
Thank you from my
Okay.
side for all the participants, and look forward to have you in the next session in December.
Yeah.
Thank you very much. Thanks, Devamoy. Thanks, Ovijit. Thanks, Chanchal. Thank you, Professor Brahmo, once again.
Yeah.
Have a nice evening.
I'm very
Bye.
grateful to hear such
Okay.
types of knowledge-based lecture. Really,
It's very interesting. Very interesting.
very interesting.
In fact, I was going back to my college days.
Okay. Yeah. But
Okay.
I'm very new with that subject, but I understand the physics from my childhood as well as from my college life. Max Planck and Einstein and the relation and how the engineers are slowly converted this in the optical fiber is really a lot of questions are arising, but out of time, I just stop now here.
Yes. Communication has moved from many. Great development in communication worldwide.
Yeah.
Absolutely.
Okay. Take care.
Okay.
Take care.
Thank
Good
you.
night.
Bye. All the best.
Yeah, good night.
Bye. Good night.